Today, I'm going to be talking to you about energy. More specifically, I'm going to be talking to you about the law of energy conservation and the different forms of energy or types of energy. Let's write those down. So, the law of energy conservation and the different forms of energy. Bear those two. So, energy. What is energy? Well, energy is actually really quite hard to describe. Um, it's something in physics which it's hard to explain in a way that's easy for you to understand. I've heard it being described as the ability of a system to perform work. That's quite a common description. But I like to think of it as a property of any object. Like if we draw a tennis ball here, um, I am really bad at drawing tennis balls, but if we just there, it's good enough. If we draw a tennis ball, this tennis ball will have a number of different properties, such as size, temperature, mass, shape, color. It'll have all sorts of different properties, and one of those properties will be energy. So this tennis ball has size, it has mass, it has color, it has shape, it has temperature, and it also has energy. Right, these are all the different, well, not all of them, but these are some of the different properties of this tennis ball. And yeah, that's some of the properties. So each of these properties will be measured in something. Size will be measured in, if we're going to use SI units, size, when I say size, I mean length. Length will be measured in meters, so we'll have 0.07 meters, and mass will be like 0.06 kilograms. The color will be green. The shape will be a sphere. The temperature will be about 300 degrees Kelvin. They're the different measurements. So the energy is always measured in joules or kilojoules, but we'll just put joules for now. We don't know how much energy this tennis ball has, but it's measured in joules. So that energy is measured in joules. That was the point I wanted to make. I think earlier I said these are all measured in SI units. Well, the SI unit for energy is joules. Actually, let me just explain to you what SI units are. SI units. SI units are the standard units used internationally for measuring different things. SI, which stands for, it's actually French. It's Système Système International de Unité. Excuse my French, I'm not French, but that translates in English to the International System of Units. It is the most commonly used, most widely used system of measurement, and that's because it's quite comprehensive. It's easy to understand, and it gives a series of different units to measure a range of different things, such as length, mass, thermodynamic temperature, energy, current, which will be in amps, and all sorts of things. So that's what SI units are, and the SI units for energy is joules. And oh yes, degrees Kelvin. Actually, I think I've time to explain that as well. Degrees Kelvin. Well, Kelvin is the unit which is based on absolute temperature. So absolute temperature is the temperature when atoms stop vibrating. So 0 degrees Celsius is the temperature when water turns into ice. It's the freezing or melting point of water. Well, 0 degrees Kelvin is the temperature at which an atom, just put one atom there, yeah, whatever. It stops vibrating. So it's vibrating before, and then it stops vibrating, right? So it stops vibrating. Like if you've ever seen the particle model, if you've ever been taught it in school, it explains how solids vibrate when they're solid because they don't have enough energy to break apart. Liquids sort of stick together but roll over each other, and gases are free. They're free from each other because they have enough energy to do that. Well, absolute zeros, when they don't have enough energy even to vibrate, they just stop moving altogether. And we don't know what happens then because it's never happened on Earth, and so we don't know what happens, but we can hypothesize, and that's all that's been done about it. But also 0 degrees Kelvin is equal to about, actually it's equal to exactly minus 273.15 degrees Celsius. I don't have space to fit that in, I'm just right there. Degrees Celsius. That's 0 degrees Kelvin. So 300 degrees Kelvin is about room temperature. That's okay. We're wandering off now. We need to get back on track. So the law of energy conservation. That's the law which states about. I think I can narrow it down to 3 things. One is that energy cannot be created. 2 is that it can't be destroyed. Energy cannot be destroyed. And 3 is that it can only be transferred. Yeah. Can only be transferred, or as the name suggests, conserved. Right? Conserved, that's what it implies. Energy can't be created, it can't be destroyed, it can only be conserved. So it can switch forms. That's all it can do. It can't be created, it can't be destroyed. That's the law of energy conservation. I think I saw a very good Minute Physics video on proof of the law of energy conservation. I'll link to that in the description. But that is what it is, quite basically. The next thing we need to know is the different forms of energy. Well, energy can do a lot of things. It can be stored. It can move around. It can do all sorts of things. So scientists, physicists specifically, like to put it in a category. They like to classify it, to give it a name depending on how they observe it. I mean, all the forms of energy that I'm going to tell you right now, they're all the same thing. They're energy, but they've been given different names. They've been put in a box depending on what kind of energy they are. But bear in mind, they're all the same, and that's why all of the different forms of energy follow the law of energy conservation, and they can switch into other forms. So there are the list of the forms of energy is always changing. It's not constant. So whenever a new phenomenon is discovered in physics, which appears to violate this law, the law of energy conservation, a new form is usually added to the list in order to balance it, to make sure that the law isn't broken, because by nature, a law of physics cannot be broken. So, they can go up to 16, sometimes even more, but for secondary school, for our level of physics, all we need to know right now are 10 different forms of energy. And those different forms are as follows. I'll write them all down and then I'll explain them to you in a minute. So, we'll go through them one by one. We have kinetic energy. We have gravitational potential energy. We have elastic potential energy. we have chemical energy, we have electric energy, there's magnetic energy, there is heat energy, light energy, sound energy, and last but not least, nuclear energy. There are the 10 different types of energy that you need to know. One thing that you should know is that most people teach you 9 because they group these two, gravitational potential and elastic potential energies, as one, just potential energy that could be. So I like to put them as 2 different forms of energy, but that's up to choice. Okay, let's go through them. So first we have kinetic energy. Kinetic energy can be described quite simply as motion. It's movement. It's the movement of this tennis ball. It's the movement of my hand. All of this is kinetic energy, and very simply, it's just things moving, and things moving have kinetic energy. A more complicated concept is gravitational potential energy. Gravitational potential energy is about fighting a force, a gravitational force to be specific. So if we redraw this tennis ball here, let's redraw it. Can we just draw it like this? Yeah, just that's fine. This tennis ball. Yeah, so this tennis ball, it has gravitational potential energy. If it is fighting, if we draw this as Earth, yeah, Earth has gravity. The gravity is pulling down on the tennis ball, but the tennis ball, if it's being thrown in the air, is flying upwards. And the higher it goes, the more gravitational potential energy it gains, the more potential it has for gaining energy to fall back down. I don't think I explained that very well. Gravitational potential energy is like the higher up you go, the further away you go from a gravitational force, the more gravitational potential energy you gain. That energy is gained from whichever type of energy got you up there, usually kinetic energy. So if we have an aeroplane going up into the air, the aeroplane will have will be going up, which is kinetic energy, and that kinetic energy is being transferred into something, and that's being transferred into sound, it's been transferred into heat, but it's also being transferred into gravitational potential energy, because the further away you are, the more you have. So if you have a tennis ball that's higher up and a tennis ball that's like lower down, if you drop both, this one's going to fall more because it has more gravitational potential energy, because it's taken more energy to get it up there. That's what gravitational potential energy is. I think it's probably maybe the most complicated one out of all of these here. But if you grasp it, you'll grasp all the others. Elastic potential energy, that's a bit more easy to explain. It is like if you just imagine a slingshot, and you have rubber, and you have a ball that you're going to throw. It's just a ball you're going to throw. This elastic here has some elastic potential energy. The more you stretch it, the more elastic potential energy it has. It's simple as that. Chemical energy is energy found inside chemicals. So, as the name suggests, so energy found in aeroplane fuel, as I was saying, the kinetic energy that an aeroplane gets when it's going up comes from the chemical energy inside the fuel. So the fuel holds energy. So if you know about respiration in biology, respiration is when animals turn glucose that they obtain into energy, into food. So the formula for respiration is C6H12O6 plus 6O2 to 6H2O plus 6CO2. That's the formula for respiration. And this here is glucose, and this molecule is what releases the energy. There's energy stored inside this molecule, and it releases this energy and that's what it is, chemical energy. Right, let's just write glucose here, and that stores the energy. That stores it as chemical energy, and then that's released to be used for movement, which is kinetic energy, for warming yourself up, which is heat energy, etc., etc. Electric energy, well, most of us have electricity, and electric energy is electricity. It's the energy going through your wires as you're watching this video right now. Whatever charged your computer, it's electricity that's powering it. So that's electric energy. It's the movement of electrons through the wire. It's electricity. Magnetic energy is the energy found in magnets. It's quite self-explanatory. Heat energy is energy from heat. So a warmer cake will have more heat energy than a colder cake. So if we draw two cakes right now, right, we have two cakes, right. It's a very flat cake. Candles on them because cakes have to have candles or they're not proper cakes. This is warm. This is cold. This warm cake will have more heat energy, and that heat energy most likely came from heating it up in like a microwave. If you're reheating it, that will be electromagnetic waves coming into it, transferring it into heat energy, which brings us on to our next energy type, which is energy form, which is light energy, also known as radiant energy, and that's radiant refers to all sorts of electromagnetic waves. They all have energy which they transfer onto something else. Heat energy is also known as thermal energy, by the way. Anyway, so that's as I explained before. In a microwave, electromagnetic waves, microwaves, which is where the name microwave comes from, microwaves will be going into the cake to warm it up. So that's warming it up, turning it into heat energy. Sound energy is the energy from vibrating molecules, because sound is just vibrations really, and the more a molecule or atom vibrates, the more sound energy it has. And the last thing we have to talk about is nuclear energy. Nuclear energy is the energy stored inside the nucleus of any atom. So if we draw an atom here, this is its nucleus. This is not going to be to scale, but if this is its nucleus, it has protons, it has neutrons, just like that. Right, so it has protons and neutrons, and it has electrons whizzing around it, and 1, 2, 3, 4. So it has the same number of electrons as protons, and these are whizzing around it, and there's energy stored inside the nucleus of this. It's called nuclear binding energy, and it's the energy that's required to split this nucleus into its different component parts, its protons and its neutrons. Protons, neutrons, collectively they're called nucleons. Right, these two together, so it should be like this. They're nucleons. Together they're called nucleons. Right, so it's the energy required to split them apart. In fact, in the sun, that's exactly what's happening. In the sun, nuclear fission takes place. No, I mean nuclear fusion, sorry, not nuclear fission. What am I on about? Nuclear fusion, where hydrogen atoms are combined together to make helium atoms. So hydrogen atoms, together they make a helium atom, right? They make helium atoms. So that energy of them coming together, smacking together at a really high speed, that is nuclear energy, and that is being transformed into different kinds of energy. So light, it'll be heat coming out. So this is the output, will be heat, and as well as that, sound. I mean, if space wasn't a vacuum, the sun would actually be really loud. In fact, every square meter the sun's surface generates thousands to tens of thousands of watts of sound power. So the sun's actually quite loud, and the only input here is nuclear power. and that's nuclear energy. So what I've explained to you today are the law of energy conservation and the 10 different forms of energy that you need to know.